Welcome to Hubble's Universe Unfiltered. I'm Dr. Frank Summers of the Space Telescope Science Institute. In this episode, we're going deep. We're going to take a look at some very deep images of the universe and see the most distant galaxies that Hubble has ever seen. Also, we're going to get a little bit deep philosophically as well, because in trying to understand these images and the objects that you'll be seeing in them, we have to encounter some concepts that you really don't encounter much in everyday life. First of all, what is a deep image? Well, you think of an image as a 2D array of pixels, and it's flat. But astronomers know that the objects in those images are at many different distances, some of them very close, some of them very distant. And so when astronomers think about the depth of an image, we think about how far away the objects are. All right? And so that's what we consider deep. However, it's awfully difficult to figure out the distances to objects just by looking at an image. So really, astronomers measure the depth of an image by the faintest objects that they can see in the image. And really, that makes sense because the fainter objects will tend to be the more distant objects. Now, in the 1990s, the director of the Space Telescope Science Institute decided that he wanted to look and see the most distant galaxies that Hubble could see. He was going to take a really deep field. So the question then comes up, where are you going to look? Well, what we have here is our view of the night sky with the Milky Way strung across the center. If you had really big eyes or a really good telescope and could look across the whole sky, this is what you would see. You would see the Milky Way stretching across. And certainly if you're trying to look for very distant galaxies, you don't want to look in the plane of the Milky Way, because all the stars and gas and dust would block your view. Similarly, down here in the lower right, you can see that there are the satellite galaxies of the Milky Way, the large and small Magellanic Clouds. If you looked in those directions, well, the stars of those galaxies would block your point of view. What you really are looking for, in order to try and look as deep into the universe as possible, is a relatively empty region of the sky. You want to try and get rid of all the foreground stars and nebulae and galaxies. Well, the astronomers working on the project found one in a field right near the handle of the Big Dipper. So here are the stars of the Big Dipper, these are the stars of the handle, and these are the stars of the cup of the Big Dipper. And I always like to remind people that the Big Dipper isn't a constellation. A lot of people think it is. It's really just an asterism. And an asterism is a recognized grouping of stars, while a constellation have been defined by astronomers, and these stars are actually part of the official constellation called Ursa Major, or the Great Bear. Anyway, that's just an aside. In this spot, near the Big Dipper, right up here, they found a relatively empty region of the sky, and they were going to do a very, very deep image. Now, it's a really small region of the sky. How small? Well, we like to say that looking through Hubble is like looking at the sky through a straw. And actually it'd be a straw with a smaller diameter than this. Because when Hubble takes an image of the sky, Hubble can look at the sky more than 5 million times and never look at the same place twice. That's an incredibly small region of the sky. Well, that's what they did looking in this region. And it was actually kind of a risky observation, because we're going to be using a large amount of Hubble time. I mean, every minute of Hubble observation is precious. And this proposal was to use 140 hours of Hubble time to look at this tiny field. And since we don't know what's in this field, we weren't really sure what we were going to see. In fact, some arguments stated that, these distant galaxies would be so faint that even with the power of Hubble, you wouldn't be able to see them. Well, fortunately, the gamble paid off in spades. This is the Hubble Deep Field. It was released in January 1996, and in it, Hubble found over 3,000 galaxies. It was absolutely amazing at the time because, as I said, we really didn't know what we were going to get. Now, you can't see the galaxies very well like this, so let me zoom into this region right here. What did we find? Well, this object right here is a star. Now, if you're going to be looking at stars, that's the star that's obviously inside our own Milky Way galaxy. One of the stars that we didn't know about before. It's obviously an extremely faint star because it doesn't show up really bright in this image. This is an incredibly deep image, and to show up at this brightness, it must still be a really faint star. If it were a really bright star, it'd be blowing out the entire field, which is, of course, what the astronomers were trying to avoid. We also see a plethora of galaxies all across this field. We see galaxies that are big, and these you would expect to be the nearby galaxies. You see some medium-sized galaxies, which you'd expect to be a little bit farther away. And then you see some tiny, tiny galaxies, which you would expect to be the farthest galaxies. You're seeing galaxies really far and really deep into the universe. So the first result of this is simply that there's a lot of galaxies out there. I mean, if you consider this, that there are about 3,000 galaxies in this image, and there are, 5 to 10 million regions of the sky like this on the sky. If this is an average region, well, just do the math, and you get tens of billions of galaxies in the universe. There are tens of billions of galaxies out there, and this image showed it that there's just an awful lot of galaxies to explore. Another result had to do with the morphology, the shapes of the galaxies that we observed. Now, of course, we saw the standard galaxies that we see in the local universe. We see spiral galaxies. Here are examples of 4 spiral galaxies, and they have, varying spiral shapes, just like the spiral galaxies we see in the local universe. We also saw elliptical galaxies. Elliptical galaxies have these ball shapes. They're just relatively smooth distributions of stars. And you see a few of them, like the elliptical galaxies we know and love. And there also are irregular galaxies. And irregular galaxies don't have any regular shape, but they can have sometimes some strange shapes. So these are some of the irregular galaxies seen in the Hubble Deep Field. And you can see that they don't have the spiral structure, or they don't have the relatively smooth ball shapes that the ellipticals have. And in fact, these are actually a little bit strange even for irregular galaxies. You can see that there's a sort of a dotted structure in this one over here, or in this one down here. And there are the clumps of stars that you really don't see a galaxy underneath these clumps of stars. And, well, the reason for that involves an idea of the fact that you're not looking at these galaxies as they are now, but you're looking at them as they were in the past. This is the concept of light travel time. And I'm going to take a little bit of a diversion to go into this, just to make sure that everyone's comfortable with this idea. Now, I first encountered the idea of light travel time back when I was a kid, and I was watching the moon landings. And it was interesting because NASA Mission Control would be talking to the astronauts, and they'd be saying, "Eagle, what's going on up there?" And then there'd be a pause, and the astronauts would reply, "Houston, everything's going great." And it seems strange that there was always this pause between when Houston talked and before the astronauts talked. And it was a couple-second pause that just seems kind of strange. Later, I understood what was causing this. The radio signals from Houston have to travel the 250,000 miles to get to the moon before the astronauts hear what Houston said. And the astronauts on the moon then reply, and their reply has to travel the 250,000 miles back to Earth. Even traveling at the speed of light, it takes 1.25 seconds to get to the moon and 1.25 seconds to get back to Earth. I mean, the radio waves that they're communicating with are just another form of light, just like the normal light we see, but radio waves have a much longer wavelength. So it's standard, they travel at the speed of light. And so the round trip to go from Earth to the moon and back, even at the speed of light, took 2.5 seconds. And that's what caused the delay in the conversations between Mission Control and the astronauts on the moon. Well, the moon is our closest neighbor in space. It actually gets much bigger the further out you go in space. For example, our sun, the light we see from the sun actually left the sun 500 seconds ago. So we're not seeing the sun as it is now, but as it was a little over 8 minutes ago. Okay? And if we go further out in the solar system, we go out to Neptune, well, we're seeing Neptune not as it is now, but as it was 4 hours ago. Because the light from Neptune has to cross the solar system, and even at the speed of light, it takes 4 hours for the light to get from Neptune to Earth. And that's just the solar system. If we go out to the stars, we get some serious time. Now, many of you may think the nearest star is called Alpha Centauri. And this is a picture of Alpha and Beta Centauri. But just to be picayune, the nearest star is actually a star called Proxima Centauri. And it's a little red star that you can't see here. So here's a blow-up to show it to you. This here is Proxima Centauri. And Proxima Centauri is the nearest star to the solar to our sun. Alpha Centauri is just a little bit farther away. However, both of these stars are more than 4 light years away. That means it takes 4 years for the light from Proxima Centauri to cross interstellar space before we see it here on Earth. I sometimes jokingly refer to Proxima Centauri as the place that you want to be if you don't like the current presidential administration. Simply because the news of the last presidential election hasn't reached Proxima Centauri yet. Proxima Centauri, if they're listening to the news on Earth, they're getting news from 4 years ago, from the last presidential administration. So you can always say, hey, if you don't like the current presidential administration, go to Proxima Centauri and you'll only have the news of the previous presidential administration. Well, the stars you see in this image are all light years away. A few light years for these stars, and tens and hundreds and thousands of light years for the rest of the stars in this image. Matter of fact, if you look across our Milky Way galaxy, they extend out to about 100,000 light years away. Our satellite galaxy, the Large Magellanic Cloud, this is a galaxy that's outside of our Milky Way galaxy. This is a small galaxy that is 170,000 light years away. And you could imagine if there are civilizations there, and they're able to see Earth, what do they see on Earth? Well, it's not just the last presidential administration. They look back and they see Earth before the rise of Homo sapiens, 170,000 years ago. What you're looking at when you look out into space, you end up looking back into time. Now, the really cool thing is that the most distant object you can see with the human eye without a telescope is this object, the Andromeda Galaxy. If you look out, if you get to a really dark site and you look up near the constellation of Andromeda, in between the constellation of Andromeda and Cassiopeia, you can see a faint smudge in the sky. It won't look as good as this, but this is our nearest big neighbor galaxy, Andromeda. And the light that we see from Andromeda left it 2.5 million years ago, which means it's about 2.5 million light years away. All right? And we can go out even further than that. This is the nearest big galaxy. If we go out to the nearest big cluster of galaxies, this is an image of the Virgo cluster of galaxies, and there's a whole bunch of galaxies all over this. This is actually just the central region of the Virgo cluster. It contains about 2,000 galaxies. And the galaxies in the Virgo cluster are 60 to 70 million light years away. And again, if you think about what they would be seeing here on Earth, looking back 60 to 7 million years ago, these guys would be seeing the end of the age of the dinosaurs. Again, looking out into space is looking back into time. So they see us as we were, say, 65 million years ago. We also see them as they were 65 million years ago. And we can go much further. In looking into these deep fields with Hubble, we see galaxies not millions of light years away, but even billions of light years away. We see galaxies as they were 1 billion, 2 billion, 3 billion, many billions of light years away, which also means many billions of light years ago. We're looking out into space and back into time. And that's one of the key aspects for understanding the results of these deep fields. Now, we weren't done with the Hubble Deep Field. Hubble has improved over the years, and in 2002 we put on a new camera called the Advanced Camera for Surveys, and using the Advanced Camera for Surveys we decided we would do another deep field. Although this one's going to go even deeper, so you couldn't just call it Hubble Deep Field 2, we had to call it the Hubble Ultra Deep Field. And for this we selected a region near the constellation of Orion. If you look down here, Orion is sort of sideways compared to what you normally see it, but down here you can see the stars of Orion, and down here in the constellation Fornax they found a suitable region on the sky for viewing the Hubble Ultra Deep Field. Again, we took over a week's worth of time on the Hubble Space Telescope and looked at a tiny region of the sky very, very deeply. What did we find this time? Well, we sort of knew we were going to find some good stuff, but we found even more than we expected. This is the Hubble Ultra Deep Field, and it contains about 10,000 galaxies. Now, the size of it is actually a little bit larger than the Hubble Deep Field. It's about twice the area, but it has more than twice the galaxies because we have a new camera on Hubble, which is able to see a little bit deeper. So 10,000 galaxies, just all in just this one tiny region of the sky. That sort of ups the number of galaxies there are in the universe. Based on the ultra deep field, we sort of estimate the number of galaxies in the universe are about 50 billion. 50 billion galaxies in the universe. And the details in the Hubble Ultra Deep Field show the same thing that we saw in the Hubble Deep Field, but more. We have our big nearby galaxies. We have our medium galaxies that are medium far away. And again, these small dotted structures that are really deep in the universe. Okay? And so you got to get the idea that what you're looking out into space and back into time. So here's an illustration to give you to really cement that idea. Hubble is here looking through various galaxies stretched out across the universe, and you've got the nearby galaxies and you've got the distant galaxies. However, this is not just a measure of distance, it's also a measure of time. These galaxies are earlier in the universe, these galaxies are later in the universe. That means that if you're covering a significant number of light years in a significant number of years, these galaxies should be younger than these galaxies. So we could actually see the development of galaxies over time by looking for the distant galaxies versus the nearby galaxies. And we put together an illustration to show that. In this bottom circle, we have galaxies seen out to about 3 billion light years away. So galaxies as they are from the present out to about 3 billion years ago. And these galaxies were all selected to be relatively face-on spiral galaxies. So these galaxies look pretty much like the galaxies that we know and love in the universe, in the local universe. They've got completely developed spiral structure. They got regular. They resemble the spiral galaxies that you've seen in the grand and glorious pictures. In the second bubble, we have galaxies that were observed from 3 to 7 billion light years away, and so are seen as they were 3 to 7 billion years ago. Now, a few million years doesn't mean much to a galaxy, but a few billion years, then you start to see some changes. And you can see they still have spiral structure, but some of the spiral structure isn't fully developed. And instead of smooth spiral arms, they've started to get a little bit of clumpiness in their spiral arms. All right? And they're just they're a little less developed. And then if we go to the third bubble, we have galaxies as they were 7 to 10 billion years ago. These galaxies have just they have their cores developed, and they have just the beginnings of spiral structure, and they have a lot of clumpiness inside their spiral structure. So these are spiral galaxies that have just had the disk form, and they're starting to form their structure. So you could sort of say, all right, these are like teenage galaxies, and these are galaxies in their 20s, and these are the galaxies that are fully developed. Okay, and so we're seeing the development of galaxies across the universe, but we're only looking in one image. In one image, we're taking the most distant galaxies as the early ones, the middle galaxies as the later ones, and the nearby galaxies as the close one, and we can see the evolution of galaxies. This is really cool because, I can't look out and see the Battle of Gettysburg. I can't look out into the past and see the past here on Earth, but when I look out into the universe, I can see the past of the universe in terms of seeing the objects in the universe as they were. And that's really powerful for seeing the development of galaxies. Matter of fact, I did my PhD thesis on the formation of galaxies, and I was using computer simulations to try and see how galaxies developed over time. I would have given my eye teeth for images like this at that time, because these showed what the galaxies were actually doing at those times, and I didn't have this when I was doing my work. So this is what teaches us why these small irregular galaxies have all these dotted structures. So here's an example of the small dotted galaxies. Most of the galaxies that are small don't have really strong structure. And you can see all of this irregular structure. And what's happening is that these are galaxies that are beginning to form together. They haven't even gotten as far as, having a nice smooth development. These are galaxies where you have clumps of stars smashing together, beginning to form galaxies. So you can really call that these are galaxies in their baby years, in their toddler or childhood years. These are galaxies just beginning to develop. When we look out into the ultra-deep field, we are seeing the galaxies as they were many billions of years ago and just beginning to develop. Now, the really coolest ones, the most distant ones, are also the most boring ones. So, giving you an example of the most distant objects in the ultra-deep field, they are not any of these interesting big galaxies, but these small red dots. And there are 3 of them in this image. Let me just circle them so you can find them. All right, you got 3 small red dots. Okay, these are galaxies that are just beginning to develop. They're the most distant in space and in time, so you would expect them not to have much structure. But the question is, why are they red? That leads us to another concept and another short diversion. First of all, recognize that the universe is expanding. Okay? The universe was born in the Big Bang and it has been expanding ever since. Well, the thing is that this isn't a physical motion of galaxies through the universe. This is actually the stretching of space, stretching the fabric of space-time. And so light waves that are traveling across this space-time actually get stretched with the expansion of the universe. To give you a simple sine wave example, if a light wave has a very small wavelength as it's emitted, as it travels across the universe and as the universe expands, the wavelength of the light wave will also expand. Okay? It may start out as a short wavelength and move to a longer wavelength. Now, in the visible wavelengths, we have blue as being very short wavelengths and red as being the long wavelengths. So we've got an illustration here in which we've got this grid here to represent the expansion of the universe. We have this blue light bulb here to represent a source that's very distant, and Hubble, of course, over here as the telescope that's going to observe it. And we keep track of how the wavelength changes as the universe expands and the wave travels toward Hubble to be observed. So it starts out as a relatively short blue wavelength, and as the universe expands and as it comes across to be seen by Hubble, it expands to a long wavelength and red. Even though the entire time the object that emitted it remains blue, it didn't change color, the light from it traveling across this expanding space stretched and moved towards the red end of the spectrum. This is the phenomenon we call redshift. And redshift is just simply the stretching of light due to the expansion of space. All objects that travel across intergalactic space have their light stretched. And the more distant objects travel across expanding space for longer, therefore their light is stretched more. They would be said to have higher redshifts. So the most distant objects are going to have their light stretched the most, and that's why the most distant objects we see in the ultra-deep field are these small red dots. They're just the small dots because they're seen at very early in the universe, and they're red because their light has been stretched out of the stretched to the red end of the spectrum. And matter of fact, it's been stretched out of the visible light spectrum and even into the infrared. Hubble has a small capacity to see the near end of the infrared spectrum, and the red in the Hubble ultra-deep field is actually light that Hubble observed in the infrared. So in order to see the most distant objects in the universe, it really helps to look not just to the red end of the spectrum, but beyond the red end of the spectrum and in the infrared. Well, Hubble developed that capacity in 2009 when we put in a new instrument called Wide Field Camera 3. And Wide Field Camera 3 had an enhanced capability of looking in the infrared. So we went back to the Hubble Ultra Deep Field, and with Wide Field Camera 3, we looked in this region in the infrared to see what more we could see. Well, this is the infrared Hubble Ultra Deep Field. And I gotta say, in looking at it, it looks pretty much like the Ultra Deep Field, unless you compare it in real detail and you start to see that there are just more sources that we can see in the infrared. There are a number of sources we can see that don't show up in the visible light of the Hubble Ultra Deep Field. As a matter of fact, it's that comparison that's really important. The objects that we don't see in visible light, but only see in the infrared light, those are the most important objects for us to look at because those are going to be the most distant objects. So the search is on to try and uncover the most distant objects. And if we look in this small region up here, I can show you a couple examples. So this is that region, and there are 3 really distant galaxies in this image. Well, it's not going to be these big galaxies. It's going to be one of these small, tiny galaxies, right? I wouldn't be able to pick them out. So, of course, we have our circles to show you where they are. 1, 2, 3. These galaxies are really, really far away. In the ultra deep field, in visible light, we were able to see galaxies that were about 12 billion light years away. Galaxies, whose light has been traveling for 12 billion years across the universe. These galaxies, well, they may be up to 13 billion light years away. And you may say, oh, what's the big deal? Just going another billion light years into the universe. Well, remember, we're looking out into space, we're looking back into time, and the universe itself is only about 13.7 billion years old. So these galaxies are galaxies as they were 700 million years after the Big Bang. We're seeing objects very, very distant into the universe, very, very into the early stages of the universe. These are some of the first galaxies that formed in the universe. And it's not just 3 examples. We actually have dozens of potential candidates for galaxies seen around 13 billion light years ago. We've outlined them with these green circles here on a different view of the infrared Hubble Ultra Deep Field. We're looking out into space and we're trying to see the initial formation of galaxies. We know that in the Big Bang, there were no galaxies. The universe was really hot, and as the universe cooled and as clouds condensed and stars formed and clumps of stars then came together to form galaxies, how long did that take? Well, it appears it only took on order several hundreds of millions of years because these objects, which are actually so small that even I look deeply in this image, I can't see them. These objects are things that were seen 600, 700 million years after the Big Bang. We're seeing the beginnings of the universe. But you'll recognize that I call these candidates. I didn't say they actually were galaxies from 13 billion light years away, simply because, as I stated earlier, it's really difficult to measure distances to objects. I mean, Hubble has a really hard time seeing these objects, and the other telescopes that are doing the follow-up observations in order to determine their distances, well, they have a really hard time seeing it. And so we don't have any confirmation yet that these truly are galaxies at this distance, but I'm expecting we'll get confirmation soon. If we really wanted to see galaxies in the very early universe, we really wanted to have an infrared telescope in space. And we do have one, the Spitzer Space Telescope, but it doesn't have fine enough resolution to see these galaxies. In order to really see these galaxies in detail, we're going to need the James Webb Space Telescope, which will launch later this decade. Now, the James Webb mirror is much larger than Hubble's mirror. Hubble has a 2.5-meter mirror, whereas the James Webb Space Telescope has a 6.5-meter mirror. So it's got a lot more light collecting surface. But the important thing is the James Webb Space Telescope is an infrared telescope. It's dedicated to looking only in the infrared. Actually, it covers just a little bit of the visible light spectrum at the red end, which is perfect if you're looking for the most distant objects in the universe. So even though we found a lot with Hubble, we can expect to see more on this subject with the James Webb. In this show, we've gone from the nearby galaxies, from our Milky Way and Andromeda and out to the Virgo cluster, out to galaxies billions of light years away in the Hubble Deep Field, to 10 to 12 billion light years away in the Hubble Ultra Deep Field, and pushing out towards about 13 billion light years away in the infrared Hubble Ultra Deep Field, and we can even expect to go further with James Webb. It just goes to show you that no matter how far out in space you look and how much you find, there's always something more to discover. Thanks for joining us. We'll see you next time on Hubble's Universe Unfiltered.